Hello all, I welcome you all to the 21st lecture in this course E614. So in the previous lecture we spoke about metal insulator semiconductor junctions, and then we saw certain behavior of the capacitor at various potentials and at different frequencies. Particularly we saw that the total capacitance normalized against the insulator or oxide capacitance for V lesser than 0, where the semiconductor is in the accumulation region, will be almost equal to the oxide capacitance. And for V greater than 0, you have a small depletion, and it lies down till what we call as depletion. It keeps going down at the mild or inversion or weak inversion, and it starts rising up at the beginning of strong inversion. Now this rise up depends upon the frequency, and then we saw that it will raise up to the oxide capacitance if the frequency is low enough. Why? Because this rise depends upon you generating the minority carriers, and the interface, the charge density of the minority charge carriers at the interface will respond to the frequency of measurement, that is you will generate and recombine, right? Because you are supplying an AC field, and the capacitance depends upon the change in the charge density by applied this field. And this V, remember, it's not this V bias, but then this V is the AC field that you superimpose on the VDC bias to actually measure the capacitance. So that's something that probably I missed out telling last time. So one has to understand that the measurement of the CV happens in this fashion. So you have a DC bias superimposed by AC. So this is the ohmic contact, this is the metal, this is the gate insulator, right? So the one that we are plotting in the x-axis of this plot is the VDC, and the actual capacitance that we measure is the change in the charge in this capacitor, in this parallel plate capacitor, versus the applied AC bias, right? And this AC bias is basically at some frequency omega, and you have to generate and recombine the charges at the interface at this frequency. And that's why at high frequencies you will not be able to generate and recombine at the frequency of operation, because there is a particular lifetime, right, for the charge carriers. That's what we saw when we calculate the diffusion current and so forth. And hence at high frequencies it tends to lay flat. Now why does it lay flat? Why does it not drop down further? I mean, why will it drop down further? It will drop down further with depletion width here keeps on increasing with the applied DC, right? But that does not happen, because once you reach the strong inversion, you already have the minority carrier sheet at the interface. So you whatever change in the DC bias that you apply, that is the x-axis you change, you will still have the minority carriers here, and hence you will not change the depletion width, which will change the capacitance, because CT, we saw that it is the parallel combination of the insulator, series combination of the insulator and the depletion width, right? And hence it will stay flat. You will reach what is called as, so this is high frequency, you will reach what is called as deep depletion. You will be able to deplete it further only if you sweep the DC bias as well, in addition to the AC bias sweep that we are talking about, right? So if you sweep the DC bias as well at high frequency, then you will not be able to form the inversion channel as fast as you are sweeping the DC bias, and hence you will change the depletion with 1 WD2 such that if you sweep it, then you will see that you will, as you increase the VDC sweep range, you will reach to lower and lower frequencies, lower and lower capacitances, which is called as deep depletion, right? So I suppose now that we understand the CV characteristics in a okay-ish fashion, we are still in the ideal uh, MOS metal insulator semiconductor characteristics. There is another aspect that I would like to throw some light upon, and that is the fact that this is psi b and this is 2 psi b. Now why is this, why, what is so holy about this psi b and 2 psi b? So to understand this, we have to go back to the band structure, right? So basically we were talking about a p-type semiconductor. So this is an this is the EI and this was EF, right? And then we defined this separation EI minus EF to be psi b. And you remember from our previous treatment, right? So Q psi b is EI minus EF, and you know this P is basically Ni e power EI minus EF by KT. So Ni is basically the intrinsic carrier concentration, right? And EI minus EF is e power Q psi b by KT. So this separation basically is a measure of the majority carrier concentration in the p-type semiconductor, right? Sorry. So now when I start inverting the channel, you will know that these guys have to bend down, right? So this EI now will bend down, and this is original EI infinity, and this is the actual EI at the surface. And our actual our definition of psi s, surface potential, is minus of EI infinity minus EI surface, right, by Q. So what we mean is when psi s is equal to psi b, this means that you have this separation. So basically the band has bent so much, so the EI has moved so far away from the Fermi level, right? So that now, I mean, in the sense that you have moved now closer to the, because initially EF was moved away from the Fermi level, now you have moved closer to the Fermi level, so you have actually made the surface intrinsic. So at psi s is equal to psi b, under this situation, the surface is actually intrinsic. So you have the number of electrons and number of holes at the surface to be equal. So the semiconductor is no more doped at this particular point. And when psi s is equal to twice psi b, then you know that you have made the surface as n as the bulk is P. So as many as holes that you have in the bulk, you have as many electrons at the surface at twice B, right? So basically you have bent this exactly in the opposite direction of your doping density to make it as n type, right? And that's why you call this a strong inversion. You have inverted the semiconductor, so to speak, right? So now that we understand the ideal characteristics, now let us go and look at the non-ideal situations, particularly two things. One is, we will assume now that, so initially we assumed that the metal and semiconductor work functions are the same, right, in our treatment. So now let us say that it is not the case, right? So we have previously seen metal semiconductor junctions where they are not the same. Now we have an insulator in between. Even then, so now let us take something of this sort, and let us take this is the metal, and let's take this is the semiconductor. So this is Q psi m, and this is Q psi s, So q psi, so psi ms is q psi m minus q psi s, and we know that when these guys join, you should have you will have electrons moving from here to here. So basically the bands will bend in this particular fashion. So here we will have a band bending upwards. This is basically your q psi ms, but I guess I've drawn it for an n-type semiconductor, and we are considering a p-type now. So basically things will reverse, right? So for a p-type semiconductor, metal is here, the semiconductor has a Fermi function lower than the metal, and hence everything will bend down, right? So when you actually meet it together, and the amount that it bends is the difference in the Fermi level, right? So under these situations, the actual voltage which is taken to invert the channel, potential needed to invert, is called as a turn on voltage or threshold voltage, and it is defined as Vt is the potential on the insulator. That's what we saw before, right? The applied voltage is summation of thing on the insulator plus twice the separation of the intrinsic level from the Fermi level plus the difference in the two semiconductor Fermi functions, right? So, or basically in this it would be yeah. So this is also called as V flat band. So this is V flat band, right? And remember, this psi ms is going to be a negative value, right? Because in our p-type semiconductor, the semiconductor has a larger work function than the metal, right? So metal lies here, the semiconductor lies here. This is q psi s, this is q psi m. So psi ms will be a negative value, right? So you need to apply a negative potential for you to make it flat, and hence the actual accumulation will happen at a negative potential and not at 0, right? So this flat band is one non-ideality that we did not consider before. We assumed that the metal and semiconductor are at equal work functions. This is the first one. The second non-ideality that we will deal today is traps, charges at the interface and the insulator. In any ideal metal insulator semiconductor junctions, you always have what are called as charges. There are various sources of charges. First one is you have non-stoichiometric oxide, in the sense that instead of SiO2, which is the actual stoichiometry, right? For every silicon you have 2 oxygen, but this never happens. You typically have something SiOX, which is X varies from 1 to 2. So basically you have certain places where you have a missing silicon. So all these things will have will lead to what is called as oxide trap charges. And this is represented by QOT, whose density is written as QOT. So you have, let us take some number of places where silicon is missing, so you call it as QOT, right? The second non-ideality that you will have is called as ionic impurities. So when you actually grow the silicon dioxide, typically in a very high temperature furnace, you have some metals in the furnace which gets contaminated, which incorporates itself into the insulator. So you have some sort of an sodium plus, some potassium plus, all such kind of ions, and you have what is called, so which has a density of QM. So these are metal ionic impurities in the insulating oxide. This is an inadvertent problem. You need a really pure furnace to grow the oxide to reduce this. The third source of oxide charges is called as fixed oxide charges. These can once again be non-stoichiometric defects in the silicon. So but then these do not move and they are very close to the interface. They are called as fixed oxide charges. And the last but not the least is called as interface charges. So the interface charges, so basically if I take I'm drawing this disproportionately just for us to visualize. So let us take this to be silicon. As we saw before, you will have some charge densities which can be moved, which are oxide trap charges. This is QOT. You have metal ions, right, of density QM. All of these guys in the insulator. This is our oxide and this is our metal. And very close to the interface, you have what is called the fixed charge densities, something of this sort, okay? And you have interface right at the interface, and this we saw before, right? So typically the silicon surface has some atoms which are not properly coordinated, because some of them are bonded to oxygen, some of them are bonded to silicon itself, some of them are not bonded at all. So all these non-idealities causes some sort of charges at the interface. So you have some sort of what is called as trap densities, which is written as DIT. This is trap densities. These traps can either attract an electron or donate an electron, and then as we saw in the metal semiconductor junction, they are called in two different ways. So if it's called an acceptor trap when it has these characteristics. It is neutral when empty and negatively charged when filled. The second one is called as a donor traps, which is neutral when filled and positively charged when empty. The nomenclature is pretty understandable, right? So it acts as a donor add atom, donor dopant, as we saw before, and the trap acts as an acceptor trap because it is neutral when empty, and when it takes an electron becomes negatively charged, donating sort of a hole. But then its role at the interface a little bit different from what it is at the bulk, where it's actually used as a dopant. But we are not just talking about traps, right? And the total number of ionized acceptor traps and donor traps will give you what is called as QIT, which is a total charge density at the interface. Right? When the entire material is neutral, so let us take all of these guys are at the band gap, right? And they are evenly distributed. It's an assumption, okay? So it's assumption that all these traps are evenly distributed in energy in the band gap. For instance, I mean, what we mean is you have traps of all energies starting from bottom of the valence band to the top of the conduction band. This is most likely not true, but then it's an assumption that is made to make our calculations easier, right? So we assume that you have traps that are evenly distributed from the bottom of the valence band to the top of the conduction band everywhere, and there exists some level here which we call as E naught, where the entire material is neutral. So you always have some number of acceptor traps which are ionized, you have some amount of donor traps which are ionized, but eventually when it is not when you do not have any charges at the bulk of the material, the entire semiconductor is to be neutral, right? So you will have some level E naught where you have equal number of ionized acceptors and equal number of ionized donors, and making the entire semiconductor neutral, right? And all levels above this E naught are called as acceptor levels, and all the levels below E naught are called as donor levels. This is once again an assumption, right? So this is a simplification, because you know that you can have both acceptor and donor levels everywhere, but you make this sort of a simplification just to show that if our EF is somewhere above E naught, then you have negative total trap densities in the interface, and if your EF is below E naught, you have a total positive trap charge density at the interface. Did I make myself clear? So we have an energy level E naught at which your interface is neutral, and if our EF is at E naught, you have zero interface charge densities. But if your EF is higher than E naught, that is you put your Fermi level at a point which is higher than E naught, then you have negative charges at the interface, and if you have your EF below E naught, then you have positive charges at the interface. This kinds of give you a feel that you have donor levels below E naught, and then you have acceptor levels above E naught, right? It's an approximation. It is definitely not true, but it is just used for our simplified understanding, right? Under these situations, your net charge at the interface can be written as minus Q E naught to EF DIT D. DIT is the density of trap densities, density of traps, as we saw before. E naught to EF, you have a negative charge, and you have EF to E naught DIT D if EF is lesser than E naught, and this equation is used if EF is greater than E naught, right? So this is how the total charge at the interface is modulated, and you can obviously change EF by changing the potential, right? So basically when you change the potential, that's the only thing you do, is you move the EF up and down, right? And when you move the EF up and down, you change the effective charges at the interface, and hence when you change, so basically when you have this trap charge density, the effective capacitance or your metal insulator capacitance is represented by the simplified block diagram. So you have an oxide trap density, right? And you have the depletion capacitance. So previously we saw that the interface, so this is insulator, not the interface. You have an insulator capacitance, and then you have depletion capacitance. In the ideal situation, you have the depletion in series with the interface, right? But now that you have trap charge densities, you have the trap charges sharing the depletion charge, but then having the same potential, right? Because it sits on the semiconductor interface, so the total potential remains the same, but then it shares the charge. So you have the interface charges in parallel with the depletion, in parallel with the depletion and series together with the insulator, right? But in addition to this, we have some resistance to this interface charge densities because of the fact that it takes some amount of time to fill and to emit charges from these things, so that there is a particular frequency dependence to this. So you model this interface charge densities in this particular fashion, so that at very low frequencies, then this resistance is a frequency dependent resistance, and at low frequencies the overall model will look like this. And at high frequencies it will look like. Why? Because at high frequencies the trap densities do not change as fast as the applied fields, and hence you have only the insulator and the depletion width in consideration. Of course, here you have to look at what is the potential which is applied, do we have the charge at the interface or not, and all those things. But then this is just related to the interface charge densities, which says that at high frequencies the interface charge densities do not contribute a lot, but whereas at low frequencies you have the interface charge density in parallel with the depletion charge density, right? So with this kind of a model, if I draw the previous total capacitance normalized with the insulator capacitance, right? And then we know that it looks, this is once again for metal on PMOS, this is V equal to 0, right? And then we know that it drops like this and then goes up for an ideal situation at low frequency. Now if we have interface charge densities, we can see that all the entire plot will be shifted at low frequencies. This is non-ideal at low frequency. Why? The reason why the entire plot gets shifted is that this is not just okay. The fact that you can deplete it and then you can start inverting the channel depends upon this relation, which is V applied is V on the oxide plus psi s, right? Psi s is the surface potential. So now that you have some interface charges QIT, you have some potential related to the interface charges, which is minus of QIT by Cox. Cox is the oxide capacitance, and hence your actual surface potential now gets effectively reduced because some of the potential is shared with the interface trap densities, right? So that leads to shifting the CV plots to the right hand side if you have positive charge densities at the interface, negative charge densities at the interface. Now what happens at high frequencies? High frequencies will follow the same path, it will just not rise up, because we know that it will actually match with the previous high frequency line, because we saw that at high frequencies you have no effect of the interface charge density, and your actual model is insulator in series with the depletion width, and hence at high frequencies at higher potentials you do not actually invert the you do not invert the channel, and hence you will have a capacitance which will be equal irrespective of the fact that you have interface trap charge densities or not, right? So Now that we have seen the effect of interface tap charge densities, now let us look at effect of all other charges. Oxide charges. So we are going to club all the oxide charges such that I'm going to write Q. Q is the total charge in the oxide, which can be written as this integral, d being the thickness of the oxide, and rho of x is a total density of all oxide charges, including its sign, right? So if Qi is a total oxide charge density, Q naught, then you have some del V, which is the potential on these oxide charges, which will turn out to be minus Q naught by Ci, Ci being the insulator capacitance, right? And hence, if you have an overall positive charge at the oxide, you will have a CV. If this is your ideal CV relation, you will have a CV with interface charge, not oxide charge densities in this fashion. So you will have this del V given by this expression. If you have a Q naught to be a positive value, if you have Q naught, that is a summation of all oxide charges, to be negative, obviously you will have a shift in the other side. If you have a negative overall oxide charge, and remember, this is over and above the flat band voltage that we spoke about before, right? So your total threshold voltage now depends on to actual. So this is the threshold voltage, right? The voltage which is required to invert the channel, at what point to invert the channel, right? So Vt now depends upon the V flat band plus the oxide potential plus 2 psi b. This is the actual potential that is required to invert, plus the potential on the oxide charges, right? So you can see that this oxide charges modulate the threshold voltage, which can become a device to device variability, because when you actually have these charges, it is possible that one device have a higher charge density than the other. Hence it is always important to control the oxide charge densities to a minimal, so that you have its influence on the turn on or threshold voltage to be small, right? So with this, we will stop our treatment on oxide charge densities, and let us have a very quick introduction to MOSFET. So that will be our second part of lecture 21. So in our treatment with MOSFET, of course, many people here would have seen what is a MOSFET. So MOSFET is metal oxide semiconductor field effect transistor. We are going to deal with only long channel MOSFETs, which means that the longitudinal field is not strong enough for velocity saturation, and you are in the constant mobility limit. That means the carrier velocities are still mobility limited. They respond to the applied field, and you do not have any velocity saturation and other factors. So we will deal with all those things in the short channel effects later on, but our first statement will be in this very simplified treatment of MOSFET. So let us very briefly look at um, two type of transistors which are currently known, which is called as the field effect transistor, and you have what is called as a PET, which is called the potential effect transistor. So PET, basically our bipolar junction transistor falls into this potential effect transistor, where the current in the channel is modified by the potential, typically by the depletion width, and the current in the channel, if it is modulated by the applied field, the electrostatic field, then you have what is called as field effect transistor, right? So now let us talk about field effect transistors. They are typically in three different versions. One is called as an insulated gate field effect transistor, then you have a junction field effect transistor, then you have a metal semiconductor field effect transistor. In the insulated gate, there are two versions of this. One is a metal oxide semiconductor field effect transistor, and then you have an heterojunction field effect transistor. We know this junction field effect transistors work on a depletion. So basically here the gate or the controlling terminal is insulated from the channel in all these methods, but then here in the insulated gate it is insulated by an oxide. In the junction field effect transistor, it is insulated by a depletion width. In the metal semiconductor, it is insulated by a Schottky contact. And when it is insulated by an oxide, you can have two types of things. One is a metal oxide semiconductor. People have moved away from the metal, but still the name remains. And in the heterojunction, you have an insulation by a high band gap semiconductor. For instance, it can be an AlGaN over GaN or AlGas over gas. All these guys are heterojunction field effect transistors, where the insulation is by a high band gap material. AlGaN is a high band gap material, AlGas is a high band gap material, and such. Right? Now, why field effect transistors are as popular as they are is because it has a very high input impedance, which is understandable because the control terminal, that is the gate, is typically insulated from the channel either by an oxide or by a Schottky contact or by depletion. With either ways, you have a very high input impedance. High input impedance are very interesting for switching. It's important for amplifiers, and it also allows for impedance matching in microwave devices. So it's good for switching, amplifiers, and microwave devices. The second advantage is it has a negative temperature coefficient. In the sense that the current reduces with increase in temperature. It is important because you do not have what is called as thermal runaway. We saw in BJT what is called as a thermal instability. You remember So we saw this situation where you see that the base current increases as uh, as the temperature, as the reverse bias increases, right? So because uh, the current which is causing the temperature rise also is leading to higher currents, and hence you have what is called as a thermal runaway. Each feeds on to itself to give you what is called a thermal runaway. That does not happen in a MOSFET, because as the temperature increases, the current drops, which does not have this feedback loop causing this thermal runaway. So it's inherently more stable than BJT. The third point is you do not have a bulk majority carrier injection as in a BJT, right? So you do not have delay due to minority carrier storage. You still have inversion of the channel, right? Because but then it is localized to the surface and it can very quickly dissipate. But then if you have a bulk injection of minority carriers, like in the case of a BJT, you have a time that is required to switch it from forward to reverse, as we saw before, because of there is some charge storage time in a BJT, right? And hence MOSFETs can have a much larger, faster switching speed than the BJT, right? So there are various versions of MOSFET. I suppose you all must have seen this by now, but let us still go slowly, right? For people who have not seen this. So there are two types of MOSFETs depending upon the current conduction channel. You can either have what is called as an N-type MOSFET, where you take a P substrate and invert the surface to get an N channel, as we saw before in the metal insulated semiconductor junction, or you take or you have a P-type MOSFET, where you have an N-type substrate and invert the N-type substrate to have a P-type channel, right? So these are the two broad types of metal oxide semiconductor field effect transistors, either N or P. This N or P tells you what is the charge carrier at the interface. So we work this, the MOSFET works in the strong inversion region, and for having an N-type MOSFET, you need a N channel, so you take a P substrate and invert it, and for a P-type channel, you take an N-type substrate and invert it, right? So now there are two versions of in each of this there are two versions. Let's take an N-type MOSFET. The same thing can be repeated for P-type, so I'm not going to do P-type. For N-type, you have what is called as first a normally off transistor, which is what I described just above. So I have this kind of a characteristic. I have what is called as the drain current. Instead of the emitter and collector we saw previously, we have a drain, we have a source, and then we have a gate terminal, right? And we are talking about the drain to source current as a function of the potential at the gate. It has this kind of a characteristic, and the drain currents at the drain potential. So you have, we will see very soon what is the typical architecture, but I'm just trying to give you the feel for the various characteristics, various relationship between the currents and the terminal potentials. So it will, in comparison to the BJT that we saw, it will look something like this. These things for increasing gate bias. So at the same drain potential, if I increase the gate bias, I see an increasing in the drain current, whereas here for the same drain potential, you have very low current for some you have very low currents for some gate potentials, and then it starts to increase exponentially beyond a particular point, which is called as the threshold voltage, or this is the potential at which we invert the channel, as we saw before. The second type of transistor is called as a normally on transistor, which has a very similar behavior but then offset in potential. This is VG. This is actually I should draw it at a much larger slope. Again VT. At Vg equal to 0, I still have a very high conduction, hence this is called as a normally on. And to actually turn it off, you have to apply a negative gate bias to actually turn this guy off. So your actual ID VD characteristics will look similar to previous thing, but it is at this point is Vg equal to 0, and these are all negative Vgs. To actually reduce the drain current, you have to apply a negative gate potential. This is what is called as a normally on transistor. You can draw something very similar for p-type transistors as well, but then we will see it later on when we deal with these things more in detail. This is just an introductory class on MOSFETs. So next time we meet, we will go a little bit deeper on all the input-output characteristics. We will see non-idealities and such. Let's take a very brief look on the typical device architecture. So as we saw before, this is an architecture for a normally off transistor, which is what is generally used. So we have, let us take for an N-type MOSFET, you have a P-type substrate. You have a contact to the substrate, which is called as the body. You have a gate insulator. On top of the gate insulator, you typically deposit on top of the gate oxide, you have typically a metal or heavily doped poly silicon or a silicide layer. It has to be a very heavily doped or highly conducting layer. We'll see the reasons for this soon enough. We typically terminate the transistor laterally by an oxide layer here. You have what is called as a diffusion to create contacts for the source and the drain. So this is a source of the transistor, and you have a drain of the transistor. We typically ground the source of the transistor, right? So when we apply a positive bias at the drain, I suppose you remember that if I apply a positive bias, you typically lower the work function, right? And you make this now smaller than the source so that the electrons can now move from source to the drain. That's the reason why you typically call this source, because the electrons will move from the source to the drain. Now because there is a potential difference between the source and the drain, applying a positive potential reduces the work function. Work function is typically from reference to the vacuum, right? So that is now much easier because it is one thing common to all the devices here. And this terminal, the metal is called as the gate, which is connected to the gate potential Vg. And if you apply sufficient potential on the reverse side, you will be able to generate a channel. The inversion layer is typically called as a channel. It is this separation which is called as the length. This is typically a three-dimensional geometry. right? And this is called as the width of the device, right? The thickness, that is whatever that goes inside this video, is the width of the device. And I suppose that's it, right? These are the only parameters that you have in this metal oxide semiconductor transistor. So the next time we meet, let us look into the various uh, conduction characteristics of this MOSFET. We will see sub-threshold current conduction, input-output characteristics and such. And finally, we will take a look at other short channel behaviors, and we'll close with a very small discussion on heterojunctions. With this, I will thank you for the attention. Bye-bye.